Well, good morning, Chemistry 20s. Today, our topic is intermolecular forces. Intermolecular. So, two different words here, inter and intramolecular. What does that mean? Well, intermolecular means between two or more different molecules. These are very weak forces, and there's an attraction between these molecules over great distances. Spelling error there, sorry. These intermolecular forces explain physical changes in properties, things like boiling point and melting point. The three main forces we're going to learn about today are the London forces. Those are the weakest of the intermolecular forces. Dipole, kind of medium strength ones that are found in all polar molecules. And then the strongest ones, the hydrogen bonding force. So how is an intermolecular force different than an intramolecular force? Well, an intramolecular force, you already know about these. These are within molecules. They are strong because they're attraction over very tiny distances, right? Like between two atoms in a molecule. This explains chemical changes in properties, like how a molecule reacts, how come it's flammable. So you already know these two main forces. Covalent forces, that's between nonmetal and nonmetal that share electrons. And also, you know of ionic forces, and those are a type of intramolecular force between a metal and a non-metal where there's a transfer of electrons. Okay, so intermolecular versus intramolecular. So again, intra is within a molecule. So two hydrogens in a diatomic molecule, hydrogen, it's inside there. The attraction between these two hydrogen molecules along a greater distance, well, that is an intermolecular force. All right, so the first type of intermolecular force that we need to learn about is called a London force or a London dispersion force. These are found in all molecules. Why? Because all molecules have electrons. Every atom has electrons. So to count up and to decide how big of a London force you have, you're counting all of the electrons in that particular chemical, all the electrons, not just the valence electrons, but all the electrons. So let's explain. How do you get this London force? It's a momentary, a temporary, or an instantaneous dipole, an attraction between the two ends of a molecule. So here's, for example, a hydrogen molecule, H2. The electrons are moving around. So if you look at a hydrogen molecule, at one instant, the electrons are over here, and then they move around, and now they're over here, and now they're over here. So the electrons are always moving around those particular, any molecule. So let's say that at one instant, and if I could freeze this molecule and the electrons were frozen in time at this end of a molecule of hydrogen, and at the very same instant in another hydrogen molecule, the electrons were frozen just in time for an instant, a second at this end, that makes a more negative, a partial negative charge end at this end of the molecule and a partial positive end at that end of the molecule. We call that a temporary or momentary dipole. So now between these two hydrogen molecules, the more negative end is attracted to the more positive, right? Negatives and positives attract to one another. This intermolecular force here is what we call a London dispersion force. That temporary, just momentary, instantaneous attraction between a positive and a negative end of a molecule. And they're not actually positive or negative charges, right? It's just because there's more electrons moving around those atoms at one instant in time. So again, London forces are in all molecules, and you count all of the electrons up to figure out what your London force is. London forces are the weakest of all the intermolecular forces. So if you're ever asked to rank them, they go at the bottom. They're the weakest. Okay, so the next force that I want to talk about is this guy, and this is the dipole. And these are only found in polar molecules. They're stronger than London forces, so they have medium strength. These, again, are only in polar molecules. So my example over here is hydrogen chloride. And you can see that there's a bond dipole. The electronegativity difference here is a value of 1.0. That puts us into the polar bond range. So we know we have a polar bond. It's a diatomic molecule. It's not symmetrical. This is a polar molecule. So what do we see here? We see that the electrons are spending more time around the chlorine end of the molecule. That makes it more partially negatively charged. The hydrogens don't attract electrons as well because they have a lower electronegativity, so they end up being partially positive. So that means there's an attraction. Here is the dipole-dipole force between these two molecules. The negative end of one chlorine HCl molecule and the positive end are attracted to one another. That is an intermolecular force that we call a dipole-dipole. Again, only in polar molecules, polar compounds. Okay, so now we are going to look at an example of how a physical property like boiling point is determined by these intermolecular forces. So the more London forces that you have in a molecule, the larger the molecule, the more electrons, you're going to have a higher boiling point than a smaller molecule. Why? Because it has less London forces, because it has less electrons. So here's an example from our group 14 of our periodic table. And we see that at the top of the group is carbon, and then as we work our way down, the atoms get larger. Carbon, silicon, germanium, and tin. So we can count up, remember this is London forces, we're counting the total number of electrons. So you look on your periodic table and carbon, it's atomic number 6, that's 6 protons, also 6 electrons. Hydrogen, atomic number 1, 4 of them, add them up, and so that's how we get this number of 10 electrons. So silicon is a larger central atom, so it has more electrons, more electrons, more electrons. What's happening to the boiling point? Well, as we're increasing in the size of the molecule, we have an increase in the boiling point, right? It goes from negative 160 to a less negative value. The number is getting higher. So again, electrons, total count, not just valence, all of the electrons, you add them up, and that is going to give you what you have for a London force. Okay, so those are our first two forces, our weaker forces, London being the weakest, dipole-dipole being the next one. Now, I want to look at what is an isoelectronic molecule. Well, it's a molecule that has the same number of electrons. Iso means same. So you would think if it was just two molecules that had the same number of electrons, they would have the same London forces. So you'd be right. But I'm going to throw a twist at you. If one of the molecules is polar and one is nonpolar, then which one has a higher boiling point? Well, I'm comparing for you here ammonia and methane. So here is ammonia, NH3, 1N, and 3 hydrogens. It has 10 electrons. Now let's compare to our methane molecule. Oh, look at that, 10 electrons. These guys have the same number of electrons. These guys are isoelectronic. Now let's look at their structures. We know that ammonia is trigonal, pyramidal. It has bond dipoles. You can see there's an electronegativity difference between the nitrogen and the hydrogen, and that creates a polar molecule. And this is not symmetrical. Remember, it has this giant lone pair of electrons here, so we have a polar molecule. On the other hand, over here with methane, tetrahedral structure, there are no bond dipoles, only difference of 0.4 between the carbon and the hydrogen. It is a symmetrical molecule. This is nonpolar. So which guy is going to have the higher boiling point? If you said ammonia, you guessed correctly. Why? Because it doesn't just have the one force, the London force. It has a second force. It has the dipole-dipole. This guy now has a dipole-dipole. This guy does not. This guy has now 2 of our intermolecular forces, so he's going to have the higher boiling point. Okay, so if you have one molecule that's polar and one that is not, the polar molecule has an extra intermolecular force. Therefore, it is going to have a higher boiling point. Okay, next up, let's take a look at the last and third intermolecular force. This is the hydrogen bonding force, the third one we're going to be studying today. This one is the strongest intermolecular force. Now, how do I know that I have an intermolecular force? Well, let's take a look here. Here's some water molecules. So I see an O and the H. This is a V-shaped molecule. This is a covalent bond. Joining the nonmetal and the nonmetal, the attraction between the hydrogen and that very highly electronegative oxygen atom, that is a covalent bond. This is an intramolecular force. A covalent bond is intramolecular. How do I know I have an intermolecular hydrogen bond? I have three possible situations where you're going to see hydrogen bonding. I use this to remember it. Hydrogen has FON. Either hydrogen is bonded to, covalently bonded to fluorine, or an oxygen, or a nitrogen, FON. Hydrogen has FON. So here we've got our first condition, hydrogen bonded to that very highly electronegative atom. So where is the hydrogen bond? It is this attraction here between the very electronegative oxygen atom of one water molecule and the slightly positive hydrogen in the other water molecule. This is the intermolecular force between two different water molecules, and that's what creates such a high boiling point. The more intermolecular forces you have, the higher the boiling point. And hydrogen bonding, being the strongest of those three intermolecular forces, means you're going to have, it makes the biggest difference, and you're going to have the highest boiling point. So let's take a look now at a couple of questions. This has some good little summary here. It goes through the intermolecular forces. And again, if you're asked to rank these forces, hydrogen bonding is the strongest, dipole-dipole, the polar molecules, medium, and London force that all molecules have because all molecules have electrons. That is the weakest force. So what happens if I have a question and it asks me to decide, is there a London force, or is there a dipole-dipole, or is there hydrogen force? Well, you know what you have to do? Any question about intermolecular forces, you got to draw out the stereochemical diagram of the molecule. So here's an example that it's asking about only London or only London dispersion forces. Look what I had to do to answer this question. I had to draw out each of my molecules. So here's ammonia. Here is C6H14, and I didn't bother with the stereochemical diagram of that. I know that that's going to be a tetrahedral molecule. Here's the tetrahedral molecule CH2F2, but we clearly know that this one is polar because of those fluorines. And then C4H9OH, polar because of the OH at the end of the molecule. What have I done? For each and every one of these questions, you count up the number of electrons and determine what is the London force. 10 on this guy, 50 here, 26, 42. So if we're just looking at London forces, ammonia has the least. But then there's other forces to consider. So then once you've drawn out, you look and see, well, yeah, this guy's polar, this guy's not polar, this guy's not polar, and this guy is polar. Oh, sorry, this guy is polar. Hydrogen bonding. There is two molecules here. There's an N to an H. Remember, hydrogen has FON, and so we have the N to the H, and the hydrogen bond would be between another ammonia molecule, and this would be the hydrogen bond between those two molecules. Okay, so that guy has a hydrogen bond. This does not. This has got a hydrogen bonded to carbon. That is not one of the guys that gives us a hydrogen bond. This guy does not have a hydrogen bond. We have a C to an F, but there's no H to an F. And this has a hydrogen bond because there's an OH. So the question was asking which guy has only London forces. The guy that only has London forces was C6H14. So each and every question you do, you're assessing counting the total number of electrons to decide what is my London forces. Is it polar or not, to determine if it has a dipole-dipole, and is the hydrogen having Fon. Okay, you guys now have some practice problems to do and a worksheet. And that worksheet is going to go through, and again, drawing those dipoles out, drawing your stereochemical diagrams, assessing, is there London forces, is there dipole-dipole, and or is there hydrogen bonding. We'll talk to you later.